Welcome to part 4 of Unit 17, where we're going to discuss esters. And esters are carboxylic acid derivatives where the OH has been replaced with OR. And esters can either come in linear or cyclic esters. If they're cyclic esters, they're called lactones. And these compounds are extremely important in biologically active compounds as well as flavors and fragrances. So how do we prepare esters? Well, one way to prepare an ester is to take an acyl chloride and to treat it with an alcohol. So here we've got a generic acyl chloride, and if we treat it with our generic alcohol, we will make an ester out of that. We need to use pyridine as a non-nucleophilic base. Specific example here, we've got an acyl chloride derivative of naphthalene, and if we treat it with isopropyl alcohol with pyridine, we will make the isopropyl ester shown here. And so, what's the mechanism of this process? Well, it follows the same general mechanism that we saw earlier in this unit, and it's an addition-elimination reaction. So again, we'll start with a general acyl chloride, shown here. And we're going to react this with some alcohol. Shown here. And first thing is addition. Attack the carbon of the carbonyl. That yields a tetrahedral intermediate. We'll draw here. R, carbon, O, minus chlorine, oxygen of the alcohol that attacked, R prime, plus charge on that oxygen. Our tetrahedral intermediate is going to collapse at this point in time, kicking off the leaving group. In this case, it's chloride. That gives us the following. And this is where the pyridine comes into play. It's going to deprotonate the oxygen here. Come in, grab that hydrogen, and at this point that yields our final product, which would be an ester. So again, this mechanism that we just drew is no different than the general mechanism of acyl substitution that we drew in the previous unit. So here, O, R prime, and there's our ester. So let's zoom out, and you can see, again, nucleophile adds, makes a tetrahedral intermediate, which collapses, kicking out our leaving group. In this case, it gives us this penultimate product, which will need to be deprotonated by a non-nucleophilic base, in this case pyridine, to give us our final product, which is an ester shown here. Esters can also be prepared from anhydrides. Again, anhydrides are reactive towards alcohols, and so here we've got an anhydride. If we react this with an alcohol, the alcohol will add to one of the two carbonyl carbons, and the other one will act as a leaving group and be expelled to give as the final product our ester plus a carboxylic acid as a byproduct. So in this example shown here, we've got an alcohol treated with acetic anhydride, and we make our ester shown here plus acetic acid as our byproduct. So again, the mechanism for this process is the same as we've seen before, except in this case we're going to have a much larger leaving group, right? We're not going to have a chlorine being expelled, we're going to have an acetate anion being expelled. So if we draw this out, again we'll use a generic anhydride, shown here. carbon, R, and if we've got our alcohol will act as a nucleophile, and it's going to add to the carbon of our carbonyl. Electrons roll up onto onto that oxygen, since we're attacking this carbon of this carbonyl, and that will provide the following tetrahedral intermediate: carbon O minus, O, carbon, R, and in this case, this piece is going to be our leaving group, and so when the tetrahedral intermediate collapses, it's going to kick out acetate anion as our leaving group, like so. Providing the following penultimate product: R prime H. So we've got a protonated ester, and in this case what will happen is, if you notice, we didn't have pyridine, and the reason for that is we don't need it. We've got the acetate anion that was expelled as the leaving group, in this case, can act as the base, like so, providing our final product, which is an ester. R, carbon of the carbonyl, R prime, and there's our final product. So if we, and plus, don't want to forget this, our carboxylic acid. So if we zoom out, you can see, again, no difference than our general mechanism. Nucleophile adds, we make a tetrahedral intermediate, it collapses, expelling this leaving group to give us, after deprotonation, our final product shown here. You can also create esters through the use of an acid catalyst. You can take a carboxylic acid and you can treat it with an alcohol with the addition of an external acid, such as typically H2SO4 is used. And what we'll do is we'll do a condensation reaction where we add on our OR. This is called a Fischer Esterification. So specifically here we've got this carboxylic acid. We're going to treat it with 1, 2, 3, 4 propanol, and under heat, and our acid is going to be H2SO4. You don't need much of this catalytic amount, and what will happen is we will lose water and we will make our ester as our final product. And so on the next slide we'll discuss the mechanism of a Fischer esterification. So as we saw in the previous slide, we can take carboxylic acids and treat them with an alcohol under acidic conditions to form esters in a reaction known as a Fischer esterification. So how does this reaction work? Well, let's take a look. It's a little bit different than our addition elimination reaction. Those pieces of that type of chemistry are part of the mechanism. It's just a little more drawn out because we're under acidic conditions. And so if we've got some carboxylic acid, like the one shown here, And we treat this under acidic conditions. The first thing that will happen is we're going to protonate, and typically we're going to protonate the oxygen of the carbonyl. So we have H3O+. And our carbonyl oxygen will swing out and grab one of the hydrogens off of H3O+. These are all under equilibrium conditions. That will give me a protonated carbonyl. Shown here. And this protonated carbonyl then, the carbon of that is much more electrophilic, and therefore if we've got a nucleophile around, in this case our nucleophile is going to be our alcohol. We typically run this reaction, the solvent for it is the alcohol that we plan on making into the ester. And so our alcohol will attack, electrons will roll up onto the oxygen. That produces the following. OH. And at this point in time, we're going to do a proton transfer. This guy needs to be deprotonated, and one of the two oxygens here needs to be protonated. And so we can show them both in the same step. So here we got H3O+. We'll show this oxygen being protonated. It does not matter. It could be either one of these two. And we can show this guy being deprotonated. Like so. And that will provide the following intermediate. Shown here. Like so. And at this point in time, what can happen is, and we've seen this previously in other mechanisms and other units, this OH, the oxygen of this OH can use its lone pairs to swing down and reform our carbon-oxygen double bond, reforming the carbonyl, and something's going to leave as a leaving group. In this case, we're going to kick out water. So this is where the condensation portion of the name comes from, because we're creating water. So these electrons swing down, that kicks out water to provide the following. Our carbonyl has now been formed. It's protonated, but it's there. And we have OR prime. And the last step of this mechanism would be then deprotonation of our carbonyl oxygen, and that can be done by the solvent, which is an alcohol. You could also show it water, because we are expelling water in this step, so water could also do it. The reason I don't show water is there's a lot more of our alcohol around than there is the water that's been created. So this swings over and grabs the hydrogen. And that yields our final product, which is an ester, shown here. prime, and there's our final ester. So if we zoom out and take a look at this, under acidic conditions, first step is going to be protonation. This activates the carbon of the carbonyl for nucleophilic addition or nucleophile adds to give us this intermediate shown here. Our OR is going to be deprotonated. One of the two OHs is going to be protonated, does not matter which one. And at that point in time, we now have a good leaving group here. The other OH will use the oxygen of the OH will use its lone pairs to swing down and reform the carbon-oxygen double bond, the carbonyl, kicking out water to give us our protonated ester shown here, and that then can lose a proton to the solvent to give us our final ester shown here. And so that's a Fischer esterification. It's a fairly simple reaction to run, and because it's under equilibrium conditions, you can play with the reaction conditions to push the reaction to give you the desired product. Now, the one thing that you have to keep in mind, especially when running a Fischer esterification, is that it is very susceptible to steric effects around the reacting site. So tertiary alcohols, it's very difficult to create tertiary esters this way. So a T-butyl ester you would have a hard time making that under Fischer esterification conditions. And one of the main reasons is that it's so sterically hindered that other side reactions can take over before you actually get the esterification. In the case of tertiary alcohols, you'll eliminate and dehydrate the alcohol first to give us alkenes instead of giving the desired Fischer esterification products. Now, if you've got your alcohol in the same molecule as your carboxylic acid and you treat it under acidic conditions, you can do a Fischer esterification intramolecularly to form a lactone, like the one shown here. And that's one way to make lactones, is to take molecules that have OHs and carboxylic acids and treat them under acidic conditions, and they will close to form a lactone. Lactones of ring sizes 5 or larger are much more easily made and isolated. Smaller ring sizes are going to be a lot more strained and more susceptible to nucleophilic opening of the lactone. Esters and lactones play major roles in biological systems, from fats and oils to vitamins to antibiotics. So here's a fat or an oil. Here we've got fatty acids, and fatty acids typically are combined with glycerol to form esters of glycerol, and this is what would be a fat or an oil. And you can see here's the ester portion of our lipid. Here we've got vitamin C, which is ascorbic acid. You can see here we've got this is an ester, it's a lactone. And here we've got erythromycin A, which is a macrolide antibiotic. It's a large ring antibiotic. And what it does is it kills bacteria by reducing the production of key proteins that the organism needs to survive. And so you can see here is the lactone of our erythromycin A. It's a large macrocycle lactone. Let's talk about reactions of esters. One reaction of esters is what's called transesterification. And a transesterification is where if we were to take our ester and we were to redissolve it into another alcohol under acidic conditions, we will swap out our alcohol piece here for whatever our alcohol is in solution. So if we take this ester, we dissolve it in methanol under acidic conditions, we will swap out this propyl piece for a methyl piece, and this is called a transesterification. Another reaction that esters can do is called saponification or hydrolysis. And ester bonds are quite labile. especially under basic conditions, aqueous base. And what will happen is, if we've got our carboxylic ester and we treat it under aqueous basic conditions, we will cleave our OR group to give us our carboxylate. So what's the mechanism of base catalyzed saponification? Well, here we've got our ester. Again, it can be a generic ester. This mechanism will work for all esters, or almost all esters. OR. And under basic conditions, we're going to have hydroxide. And our hydroxide is a nucleophile, and it will add to the carbon of the carbonyl. The electrons will roll up onto the oxygen of the carbonyl, and that will yield a tetrahedral intermediate. Shown here. OR. OH. And again, our tetrahedral intermediate isn't going to last very long. It's going to collapse. And when it does, something's going to get kicked out. Well, the better of the two leaving groups here is actually going to be the OR. We're going to kick out OR in this case. Yielding our carboxylic acid, which under basic conditions is not going to stick around very long. It will be quickly deprotonated. So we have OH. We just eliminated OR, so alkoxide, an alkoxide base, which on its way out can steal that hydrogen to yield as the final product our carboxylate. Shown there. And that is the base catalyzed hydrolysis or saponification of an ester. We can also reduce esters using dibal. So if we've got an ester and we treat it with dibal, we can reduce the ester by adding a hydride in the place of our OR to give us aldehydes. So this is a nice reaction to convert esters to aldehydes. Now, under biological conditions, esters are also hydrolyzed, and typically these are done by a variety of enzymes. Here's a specific example. This is acetylcholinesterase enzyme, which will hydrolyze the neurotransmitter acetylcholine, and this is done in order to terminate a neural impulse. And the way this works is as follows. We've got abstraction of this hydrogen, which makes this into a very good nucleophile. So we're making the enzyme into our nucleophile. It attacks. Electrons roll up onto the oxygen. That gives us the following tetrahedral intermediate shown here. This doesn't stick around very long. It collapses, and when it does, this OR group is removed. And so as it's removed on the way out, it grabs a hydrogen from a nearby acidic functional group. That yields the following ester. So we've got our ester here. Our R group is actually the enzyme, and this isn't going to stick around very long because in a sense we've got our substrate bound to the enzyme, and our enzyme now is going to be the leaving group. And so what we need to do is add OH to this, and so a basic functional group will abstract a hydrogen from water. That will allow it to add to the carbon of the carbonyl. yielding again a tetrahedral intermediate, which isn't going to stick around very long. It's going to collapse, and when it does, it kicks out the enzyme as the leaving group. And as it does, the oxygen that's part of the enzyme is going to pick up a hydrogen for a nearby acidic functional group to regenerate the enzyme and to yield our desired product here, a carboxylic acid from our ester. So if we zoom back out and take a look at the whole process, it's no different than what we were just drawing. It's just that it takes a couple more steps to do it because we don't want to have very reactive reagents around like hydroxide. Those have to be created in the vicinity of our ester, and we have to actually activate our ester so that it has a good leaving group on it. And in this case, our leaving group is actually the enzyme in this final piece right here to give us our carboxylic acid as the product in the end. This brings us to in-class problems 17-3 and 17-4. So let's take a look at these. 17-3, what I'd like you to do is provide the mechanism for the following base catalyzed lactone hydrolysis. So lactones are esters. They can be hydrolyzed just like an ester. In 17-4, what I'd like you to do is provide the step-by-step mechanism for the following transesterification. And so this would be a good time to pause the videos and work on them yourselves, and then we'll come back and do it together. Okay, now that you've had some time to work on these, let's go through them together. So let's take a look at the first one. Here we've got a lactone, and lactones are just esters, except they're in a ring. And so the hydrolysis under basic conditions of a lactone is going to be very similar to that of any normal ester. And so here we've got hydroxide. It's going to add to the carbon of the carbonyl. Electrons are going to roll up onto the oxygen. That will provide the following tetrahedral intermediate. Minus OH. And when this collapses to reform the carbonyl, it's going to kick out and open up the ring like so. And that will yield our open product. OH, a minus charge here, and this guy will pick up a proton from the solvent, which in this case is water. Like so. Boom. Boom. And that gives us our final product shown here. OH and our carboxylic acid. And so that is base catalyzed hydrolysis of a lactone. Now let's take a look at 17-4, which is drawing the mechanism of transesterification. This one's a little more complicated. So let's draw out our ester again. CH3. And we're under acidic conditions in ethanol. So the first step, if we're under acidic conditions, is that this is going to be protonated. And And so you can have this. I'm going to abbreviate this as ethyl. And what happens is when we add in acid, we protonate the solvent, because ethanol is like water, so it'll be protonated, and our oxygen of our carbonyl will grab a proton from our protonated solvent, and that yields the following. Like so. And what happens here is now our solvent can act as a nucleophile, so in this case it's ethanol. Again, I'm going to abbreviate as ET, and it will add to the carbon of the carbonyl because it's much more electrophilic now because it's been protonated. Giving us the following. O-methyl. Gives us this cation. And we're going to do a proton transfer here. Now, the interesting thing about this is what's going to be protonated and deprotonated. Well, we know what's going to be deprotonated, right? This is going to be deprotonated. In this case, though, this piece is actually going to be protonated. The oxygen of our other OR group. And so here's what's going to act as the base. It's going to be ethanol. Come in and grab that proton. And this oxygen will pick up a hydrogen, a proton from protonated ethanol. Like so. And that gives us the following intermediate. That. And what will happen here is that this oxygen will swing down and kick this out. It's going to reform our carbonyl like that. Boom. Kicks that piece out. And we're almost home. This is back our protonated carbonyl. O ethyl. And then the final step will be deprotonation by a solvent molecule, which would be ethanol. Like so. Bang, bang, and that gives us our final ester product, which is a new ester, or ethyl ester in this case. Like that. And if we zoom out and take a look at the overall process, we're under acidic conditions. So the first step is going to be protonation of the carbonyl oxygen. That allows then for this carbon of the carbonyl to be much more electrophilic, so our solvent, in this case ethanol, will add. That gives us this tetrahedral intermediate shown here. And at this point we need to go through a proton transfer. Hydrogen off the oxygen of our newly added ethanol needs to be removed. Our methanol piece here, the oxygen of that needs to be protonated. That gives us this intermediate shown here. The OH lone pairs will swing down, kicking this out as a leaving group, giving us our next to last product, or our penultimate product, which would be the protonated ester, and this will quickly lose a proton to give us our final new ethyl ester. And so that's the mechanism for transesterification.